Hello students, so today we are going to discuss about hydrogen peroxide. Known use of hydrogen peroxide for us is to make wounds free from germs. First, we need to clean the wounds with hydrogen peroxide to make it free from germs and then we can apply medicines. Other than that, as mentioned, it is important chemical to use in pollution control treatment in domestic and in the industrial influence. So it gives same type of effect. When hydrogen peroxide reacts, it leaves nascent oxygen, that means single oxygen atom. From H2O2, it will convert into H2O and it releases single oxygen. So this single oxygen is highly reactive, so it will react with anything which comes in contact with it. If it comes in contact with germs or small organism like bacteria or viruses, it will come in contact with it and it will destroy their structures. Similarly, pollution causing particles will come in contact with oxygens and it will convert in some simpler molecules which cannot cause harms. If we talk about the physical property of H2O2, then it is almost colorless. It has very pale blue color, but it seems almost colorless just like water. Its important physical properties are mentioned in table 9.4. Now, when we get H2O2 for industrial or domestic use, it comes with new type of concentration. Commonly, we are familiar with mole fractions or molality, etc. But in this case, we have percentage solution of H2O2. So H2O2 is soluble in all the proportion with water. That means if you use higher quantity of water or higher quantity of hydrogen peroxide, doesn't matter, they will mix with each other to create a uniform solution. So 30% solution of H2O2 is marketed as 100 volume. So what it means, if you have 1 liter of H2O2, it will produce 100 liters of oxygen gas, then it is called 100 volume. So if we have 30% solution of H2O2, it can produce 100 times more oxygen than the quantity or volume of H2O2 solution. H2O2 solution will be in liquid form and produced oxygen will be in gaseous form. And commercially marketed sample is 10 volume. That means it simply produces 10 times more volume of oxygen than the solution. So it means it will be 3%. If we have 30% solution which is 100 volume, then 3% solution will produce 10 volume of H2O2. To understand this, first we need to see the reaction of H2O2. When H2O2 leaves in open atmosphere, it will produce water molecules and oxygen gas. So if we balance the chemical reaction, then we need 2 moles of H2O2 to produce 2 moles of water and 1 mole of oxygen gas. Now let's put some different values for reactants and products in this reaction. So first, weight or mass. We have 2 moles of H2O2. So 1 mole of H2O2, that means it has 34 gram. That means molar mass of H2O2 will be 34 grams. Here we have 2 moles, that means 34 multiplied by 2, that means 68 grams. So we have 2 moles of H2O2, it represents it has 68 grams of mass. Then we have 2 moles of water, 1 mole is equal to 18 grams, we have 2 of it, so we have 36 grams of water. And then we have 1 mole of oxygen, so simply it will be 32 grams. So we have 68 grams of reactant and total we have 36 plus 32, that means again 68 grams of products. If we place number of moles, they are already mentioned. We have 2 moles of H2O2 which produces 2 moles of water and 1 mole of oxygen. So number of moles, and last thing, volume. Now water and H2O2 both are in liquid state, so we cannot measure their volumes directly, but we have oxygen in gaseous state. So according to STP, 1 mole of gas is equal to 22.4 liter gas. So we have 1 mole of oxygen, that means volume of this 1 mole of oxygen will be 22.4 liters. So simply, if you have 68 grams of hydrogen peroxide, it is able to produce 22.4 liters of oxygen or 32 grams of oxygen. Now with this relation we can calculate the volume or percentage of hydrogen peroxide solution. Just keep in mind this relationship: 68 grams of H2O2 is equal to 32 grams of oxygen or 22.4 liters of oxygen and vice versa. Now based on this equation, let's calculate the numerical mentioned here. So problem number 9.5, calculate the strength of 10 volume solution of hydrogen peroxide. So we have 10 volume H2O2 solution. So it simply represents, if you have 1 ml of H2O2, it can produce 10 ml of oxygen gas, 10 times more gas or 10 times more volume of oxygen. And as we discussed in our equation H2O2, we need 2 moles of H2O2 to produce 1 mole of oxygen gas. That means 68 grams of H2O2 can produce 22.4 liters of oxygen. We need to use liter for the oxygen and gram for peroxide, because volume of oxygen is mentioned in liters or milliliter. As mentioned here, we have 10 volume H2O2. So we can calculate with cross multiplication. If we have 22.4 liters of oxygen, then it can use 68 grams of H2O2 based on the equation we discussed earlier. So if we have 10 liters, later we can convert this 10 liters into milliliters, or we can do it right now, but we have to make small changes in our equation, but let's do it later. So 10 liter is equal to how many grams of H2O2? So 10 liter multiplied by 68 grams divided by 22.4 liters, and it is equal to 30.35 grams. That means if we produce 10 liter of oxygen from the given solution, it represents we have 30.35 grams of H2O2 in 1 liter of solution. So we have 30.35 grams or roughly 30 grams of H2O2 in 1 liter solution, and we can convert it into percentage. 100 ml is equal to 30.35 grams, then 1000 is equal to 30.35, then 100 is equal to how many? So simply it will be 3.035, or approximately it is 3. So we have 3% solution of H2O2. And the structure of H2O2 is two-dimensional structure. Two oxygens are attached with each other, let's say in a straight line in a single plane. Then one of the hydrogen will be in plane of the screen and other hydrogen will be above the screen, something like this. So we have two-dimensional shape, like half-folded book. Suppose this is the upper half portion of our book, and then this will be lower half portion of book. As shown in these two images, we have two different type of structures. They are identical structure with slightly change in angle and length of bonds. In gaseous phase and in solid phase, H2O2 gives two different type of structures. They are almost same type but slightly with different lengths and angles. Now let's talk about the heavy water or D2O. Just like the regular water, instead of hydrogen or protium, we are using deuterium. So deuterium particles are comparatively heavier than hydrogen or protium. That's why it is referred as heavy water. So it is extensively used as a moderator in nuclear reactor and in exchange reaction for the study of reaction mechanism. So what these 2 points means: in nuclear reaction, generally radioactive particles loses nucleuses. That means their nucleuses will burst and it will release neutrons and protons. So these neutrons and protons will collide with other nucleus and it will make them unstable, and those unstable nucleuses will release more particles. So this is the example of chain reaction. Let's say we have a nucleus which releases two neutrons. So these two neutrons will collide with two other nucleuses, and each new nucleus releases two more neutrons, and these neutrons will collide with more nucleuses, and those nucleuses will release more neutrons, and so on. So this type of reaction will lead, eventually it will lead to very high quantity of neutrons, and that's why it will release comparatively very high amount of energy, and it will lead to blast, that means nuclear weapon. So in case of nuclear reactors, we have to control these type of reactions, and that's why we need moderators. So function of moderators is they will absorb some of the neutrons from the reaction, and that's why we can decrease the speed of reaction and we can control the rate of reaction. And second thing, how can we understand the mechanism of the reaction using heavy water? To understand that, let's consider a simple reaction. As for example, we have methane gas and hydrogen gas placed in container. After some time, if we observe the concentration or quantity of hydrogen and methane, then no change appears. That means we have same type of composition, methane and hydrogen. So as we know, reactions are not static. They are not steady, but they are dynamic. They are in continuous motion. But how can we say that? So to understand this, whether anything going on with this reaction or not, we have to replace hydrogen with deuterium. Let's say we have 1 mole of methane and 1 mole of hydrogen. Now from the 1 mole of hydrogen, let's remove some of the hydrogen and let's replace it with deuterium. That means our reaction mixture contains 1 mole of methane plus, let's say, 0.8 moles of hydrogen, and now some of the hydrogen is replaced with deuterium, 0.2 moles of D2. So if anything is happening between methane and hydrogen, then as mentioned in previous case, no detection will be observed, no change will be observed. But if reaction between methane and deuterium occurs, then we can see some difference. So let's say we have CH4 with deuterium, then in this case one of the hydrogen will be replaced with D2. So possible product will be CH3D with HD. If one more hydrogen is replaced, then second possible product will be CH2D2. Then further, if reaction proceeds more, CHD3, and later finally we can obtain CD4. Just like CH4, we can get CD4. So that's how we can identify whether the reaction is moving or not, and what is the mechanism, that means which of the reactant reacts with which of the other reactant. So to identify movement of the reaction or complexity of the reaction or mechanism of the reaction, we can replace some of the particles with their suitable isotopes, and we can do it for with any other particles as well. We can do it with carbon as well. That means to identify the reaction mechanism, we can replace carbon with its one of the isotopes. It can be prepared by exhaustive electrolysis of water and as a byproduct in some fertilizers. Its physical properties are mentioned in table 9.3, and it is used for the preparation of other deuterium compounds. For example, now all the examples mentioned here are just like the reaction with hydrogen. Isotopes shows almost similar type of chemical reactivity. Their chemical reactivities are almost same, that's why just like hydrogen you will get the same type of reaction with deuterium. Main difference between the isotopes is their masses. Their electronic configurations remain same, and that's why their reactivity remains same. In their reactivity, speed may be different. That means if hydrogen and deuterium both react with same type of compound, then speed will be different depending on the strength of bond. If hydrogen hydrogen bond is stronger, then it will give us slower reaction. If deuterium deuterium bond is weaker, then it will give us faster reaction. but they will end up in same type of compound formation. As mentioned here, we have CaC2 with D2O, it produces C2D2 and CaOD twice. That means instead of deuterium, let's say we have water molecule, normal water molecule, then in this reaction our products will be C2H2 and CaOH twice. And similar type of trend will be observed here. SO3 and H2O produces H2SO4. We already know that sulfur trioxide gas with water produces sulfuric acid. Then Al4C3 12D2O, it produces CD4 and ALOD thrice. That means it produces methane and aluminum hydroxide. Then our last topic is dihydrogen as a fuel. We already know that hydrogen is flammable gas and it can release comparatively high amount of heat. So using this property of hydrogen, we can use hydrogen as fuel. But we have some problem with hydrogen and we can discuss that problem with the data as mentioned in the table. So in this table, comparison between dihydrogen in gaseous state, in liquid state, LPG, methane and octane. Octane, that means petrol. Petrol is hydrocarbon and it contains 8 carbon chain, that's why it is referred as octane. If we compare energy released per mole with this type of different fuels, then you will notice hydrogen is far behind than our traditional compounds. That means it releases 285 to 86 kilojoules of energy. On the other hand, methane releases almost 3.5 times more than hydrogen. And this figure even increases further with LPG and highest will be observed in octane. And it is obvious because in case of hydrogen we have only hydrogen, that means H2, whereas LPG uses butane, we have methane which contains 4 hydrogen 1 carbon, and octane, that means we have 8 carbons and 18 hydrogens. So it contains highest number of particles, so obviously it will release comparatively high amount of energy. On the other hand, if we observe per gram, then you will notice hydrogen is highest in this case, because in 1 gram hydrogen has comparatively more number of moles because it has lowest molecular mass, and that's why in 1 gram of quantity you can get highest number of molecules of hydrogen. It can release 142 to 43 kilojoules of energy, whereas LPG can release only 50, methane can release 53, and petrol or octane is least per gram. In per gram 47 kilojoules. But in case of liter, again you can see drastic change. For gaseous hydrogen, only per liter you can get 12 kilojoules of energy. Whereas in liquid nitrogen we can get comparatively good amount of energy, 9968 kilojoules. LPG releases comparatively very high amount of energy, 25,590. Methane releases very poor amount of energy, 35 kilojoules, and petrol releases highest amount of energy per liter, 34,000. So as we can see, usually we use fuels in liters. As for example, we use petrol in our car and usually we purchase petrol in liters because we can store it in our fuel tanks. So assume the similar situation with hydrogen powered cars. If you have hydrogen powered car which uses gaseous hydrogen, then per liter you can get only 12 kilojoules of energy and it is not sufficient. In liquid state we can get some energy from the hydrogen, which is 9968, that means almost 10,000 kilojoules, which is comparatively more than the gaseous state, but it is far more behind than the petrol. That means if 1 liter of petrol gives us 15 kilometers of the range, then with 1 liter of liquid hydrogen you can get only 5 kilometers of range, and it is not viable. That means practically we cannot use it because of very poor performance. And other problem with liquid dihydrogen is we need to store it at very low temperature. We need 20 Kelvin temperature. So first thing, it is hard to achieve. 20 Kelvin is very low temperature. So it is very hard to achieve and very hard to maintain. So first thing, you have to decrease the volume, and then we have to increase the pressure. So dihydrogen in liquid state can be stored at extreme low temperature and very high pressure. So again, to achieve the liquid state of dihydrogen, we have to apply some of the energy first, and then you can get the energy. So overall output will be reduced even further. That means almost 10,000 kilojoules of energy can be obtained per liter liquid hydrogen. But first we need to cool down it up to 20 Kelvin, and we have to apply high amount of pressure which uses energy. So it even decreases efficiency further. So these are the problem with hydrogen to use it as a fuel. First, as mentioned, very lower temperature is required, and that's why it requires expensive insulated tanks. So it increases the cost of the production, and it is not viable option. Second thing, we have other options which are easily available than hydrogen. As for example, petrol produces very high amount of pollutants. On the other hand, hydrogen produces water and some of the nitrogen oxides, but we can easily stop the production of nitrogen oxide from the hydrogen. So we can say that it is almost non-pollutant. But problem with hydrogen is it increases the cost, and second viable option from the petrol is electric car. Electric car also do not produce any kind of pollutants. That's why it is our second favorable option than the petrol. Plus point of electric car is we do not need any type of infrastructure separately, because already we have the source of electricities in our house. But with hydrogen, main problem is availability of hydrogen. First we need to put hydrogen fuel plants, and then we have to make them available for common public. So it is very hard task, and that's why hydrogen powered cars are not yet popular. In case of storage, we can use some of the alloys as mentioned here. These metals can storage hydrogens in small quantity, because hydrogen occupies comparatively very high volume. Because as we know, any gas with at STP occupies 22.4 liters, and hydrogen has smallest molecular mass 2 grams. That means 2 gram of hydrogen occupies 22.4 liters of volume. Nowadays, it is also used in fuel cells for the generation of electric power. It is expected that economically viable and safe source of dihydrogen will be identified in years to come for its uses as common source of energy, but right now we are comparatively very far from that target.